All right, welcome back, you guys. Your favorite Calculus 2 course. We're going to take a look at improper integrals. Those are objectives. If you remember a definite integral, right, integral from a to b, that required first that the interval be finite from a to b, and furthermore, the fundamental theorem of calculus also required that it be continuous. Okay. So in this section, what we're going to do is we're going to look at, so could we do it if it breaks one of those two molds? And yeah, sometimes we can. Sometimes you can. So today we're going to study a procedure for evaluating requirements that are either type 1 that have an infinite integration limit, or a type 2 where they have an discontinuity. Okay, an infinite discontinuity. So here's like a picture of an infinite discontinuity. If you approach C from the right or from the left, as you approach it from the right, it's shooting you up to infinity. Of course, as you're approaching it from the left, it's shooting you down, right? So you've got a vertical asymptote. So these are infinite discontinuities, right? And we're going to be able to do some of those. And we're also going to look at the first type we're going to look at is where you have an infinite limit of integration. So, for example, we go from a to infinity, and we're going to see if it actually converges to a finite number or not. Okay. And then you've got those other three types listed there. Okay. And do note, if the improper integral converges, or it will converge if the limit exists. In other words, we get a value for it. Otherwise, it's diverging. And in the third case, if either of these does not converge, then we just say it diverges. So if either of them go awry, oops. All right, best to look at an example here with this first one. Determine whether the unbounded area of the region on the curve y equals 1 over x squared and above the x-axis from 1 to infinity converges or diverges, right? So we're trying to find the area from 1 to infinity of this 1 over x squared dx, right? And so if I look back here, I say, well, we've never done this before. This is an unbounded or an infinite, right? This is an improper integral, right? It's not just from a to b. It's from a to infinity, right? So this is an improper integral with an infinite limit. So it's a type 1. I'm calling these a type 1 improper integral. And number 1, I'm going from a to infinity, right? And so I'm going to note this right here. I could rewrite this. It's equivalent to mathematically the limit as b goes to infinity from a to b, right? Because again, b is just infinity anyways. So mathematically, those are the same thing. Let me go ahead and note this. Note this is a type 1 improper integral. Well, the first handful of problems we'll do will all be these type 1s. But specifically, it's type 1 number 1. And so I'm going to write, what is type 1 number 1? Well, that one says that if I go from a to infinity of my function, it's equal to the limit as b goes to infinity of a to b. And so I can apply fundamental theorem of calculus on this part right here, as long as I run the limit as b goes to infinity on that. Okay. And so here's what we have, right here. So let's apply type 1 number 1. So I'm going to say, well, as long as I take the limit as b goes to infinity, I go from 1 to b. Right? Again, b is going to infinity. Then this is the same thing, right? So that's the same thing. It's a type 1 number 1. So I have the limit b goes to infinity of x to the negative 2 dx from 1 to b. And we know that we can run that integral now of x to the negative 2. So that'd be x to the negative 2 plus 1 over that from 1 to b. So we have negative 1 over x from 1 to b. Let me come over here. Now let's throw in the b. So negative 1 over b minus negative 1 over, now I plug the 1 in. So we got limit as b goes to infinity of negative 1 over b plus 1. Now as b goes to infinity, this will go to 0, right? Because b is increasing in magnitude. That's like negative 1 over this huge, huge, huge number, right? As it gets bigger and bigger and bigger, we approach 0, right? Or if you want to split these up, you can also think about it as splitting these up. And so that is a 0 and then plus 1. Well, 0 plus 1 is just 1. Therefore, so let's conclude. This improper integral converges, right, since this limit existed, and the area of this unbounded region, remember we were finding the area from 1 to infinity. So this area of the unbounded region is 1. It's a finite number. Kind of weird to wrap your head around, right? All right, let's look at this next one here. We've got another 1 to infinity here, right? So we've got another type 1. All right, we've got this improper integral with an infinite limit that we're looking at. It's also a number 1. So type 1, number 1. So from a to infinity of this function is equivalent to the limit as b goes to infinity of a to b of the function. So we're going to use that as we try and examine this area under the curve from 1 to infinity of this 1 over x dx. So let's apply type 1, number 1. And now we say, well, we know the integral of 1 over x is the natural log of x. And we're doing it from 1 to b. So we've got the natural log of b minus the natural log of 1. Well, we know the natural log of 1 is 0, right? So now let's throw infinity in. Well, if you think about natural log of x, right? Here's our natural log of x as the limit as b goes to infinity, right? This will end up being infinity, right? It gets increasingly large. And so we just got infinity minus 0, right? So we just got infinity. So this thing diverges. It does not converge to a finite value. Diverges. So the unbounded region has an infinite area, right? It doesn't converge to a finite value. Again, because that diverges. This is a good you try it problem. If you want to go ahead and pause this right here and try this problem, that'd be great. Here, if you're getting a picture of this, here's that e to the negative x, right? Reflection about the y-axis of e to the x. And you're going from 0 to infinity, right? So this is looking for, does that unbounded area is actually what we're looking at here. So this is another type 1, number 1. So we have from a to infinity of f of x dx is equivalent to the limit b goes to infinity from a to b. So here we have let's go ahead and let u be negative x, so du is a negative dx. Put that in. And so this ends up being limit as b goes to infinity of negative, and now we're going to run the integral of e to the u du. And the integral of e to the u is 1 over ln of e to the u. We know the ln of e is just 1, so we've just got limit as b goes to infinity of negative 1 over e to the x. So here we've got e to the b. This will get huge, right? So it's like negative 1 over infinity. So this will go to 0. And then we got plus 1, right? E to the 0 is 1. So we got plus 1. So we got 0 plus 1. So we got 1. Therefore, the improper integral converges. And the unbounded area, all right, we were doing this from 0 to infinity. The unbounded area is finite. And ends up being 1. Bless you. All right, let's do this next one here. All right, here we've got 0 to infinity, so we've got another type 1, number 1, infinite limit here. So type 1, number 1 again. So from a to infinity, it's the same as the limit as b goes to infinity from a to b. And so here we've got 0 to infinity of 1 over x squared plus 1 dx. So it's the same as the limit as b goes to infinity from 0 to b of 1 over x squared plus 1 dx. Now remember, if you look on your formula sheet, the integral of 1 over a squared plus u squared du is 1 over a arctangent of u over a, right? And so we can take this, our u here is the x, our a is the 1 squared, so a. And so this ends up being the limit as b goes to infinity of 1 over 1 over a, arctangent of u over a, and then from 0 to b. And so we've got the limit b goes to infinity of the arctangent of x 0 to b. And so we've got limit as b goes to infinity, the arctangent of b minus the arctangent of 0. And actually, let me, before I go there, so let's think about this for a minute. The arctangent of 0, so if you remember, the arctangent of 0 equals theta, then that means the tangent of theta equals 0. We cut off the tangent between negative pi halves and pi halves, so where would that be true? Whenever theta is 0. So in other words, the arctangent of 0 equals theta, which is 0, right? So this is This is 0. So we have the limit as b goes to infinity of the arctangent of b minus 0, right? So we're just finding the limit as b goes to infinity, the arctangent of b. And if you think about the graph of the arctangent, remember that's the inverse of the tangent, right? So if you look at the tangent from negative pi halves to pi halves and you flip every xy value around, instead of a vertical asymptote at x being negative pi halves or x being positive pi halves, you'd have a horizontal asymptote at y equals pi halves. Instead of a vertical asymptote at x equals negative pi halves, you have the horizontal asymptote at y equals negative pi halves, and you flip every point around, and there's your arctangent function, right? Arctangent of x. Well, as I run this to infinity, what does the arctangent of b go to? Yeah, pi over 2. It approaches pi over 2, right? It gets closer and closer and closer to pi over 2. So this converges. I got pi over 2 minus 0, which is just pi over 2. Therefore, the improper integral converges, and the unbounded area of the region from 0 to infinity is finite, and pi halves. It's pi halves from 0 to infinity. Interesting. So we've got an improper rule. We're going to actually have to use L'Hopital's rule when we do this. So we've got another type 1, number 1. And so we're going to go ahead and let me set this up first. So we've got 1 to infinity, 1 minus x e to the negative x dx. And we're going to set that up with our type 1, number 1 again. So limit as b goes to infinity of 1 to b of 1 minus x e to the negative x dx. So then the question is, well, how do we even do this? Well, this goes back to our integration by parts. So here's our dv part. Here's our u. So if you remember, integration by parts is the integration of u dv equals uv minus the integration of v du, right? And here we've got u being 1 minus x, dv being e to the negative x dx. And so du ends up being a negative dx. I go ahead and I integrate this. I'm going to let u be negative x. And so v ends up being negative e to the negative x. And let's go back to, so what does this end up being? uv, there's our u, there's our v, minus the integration of v du, which is a negative dx. And so we've got, let me go ahead and distribute that through. I've got negative e to the negative x plus an x e to the negative x. And then I got negative times a negative times a negative. Goodness, I've got negative e to the negative x dx. And then I'm going to let my u be that negative x. So du is a negative dx. So I need a negative. I'm going to put a negative there, which will make that a positive right there. And so we've got negative e to the negative x plus x e to the negative x. And then plus, and then we integrate e to the u. So 1 over ln of e, e to the u, and then plus a constant here. Well, this is from 1 to b. So let's go ahead and clean that up a little bit. See how those are gone. So I have x e to the negative x. So we just integrated the whole thing. So let's bring this over here. So we have the limit as b goes to infinity. We went from 1 to b of this 1 minus x e to the negative x dx. We did it with integration by parts. And we ended up getting the x e to the negative x. But we got to go from 1 to b on that. So we've got limit as b goes to infinity of b over e to the b minus 1 over e to the 1. And so we've got limit b goes to infinity of b over e to the b minus, I'm going to write this separately, 1 over e. We know the limit as b goes to infinity of 1 over e is just a 1 over e. But this one, this is where our L'Hopital's rule comes into play, because notice we have infinity over infinity. So we have indeterminate in form, and so we've got to run the derivative of the top. So the derivative b is a 1. Derivative of e to the b is ln of e times e to the b. And then minus, and then we know this all just gives us the 1 over e, right? And notice here, now as we run this to infinity, this will go to 0. So we got 0 minus 1 over e. 0 minus 1 over e, so we just got negative 1 over e. And so, therefore, the improper integral converges. And is negative 1 over e. Now this is not an area, right? Because this is negative there. This is just the improper integral, just converges. All right, let's look at one more of these type 1, number 1 here, where we're trying to find this area under the curve here from 1 to infinity of this function natural log of x over x squared dx. So we're again another type 1 and a number 1. And so we'll be using from a to infinity of the function as the limit as b goes to infinity of a to b. That's what we'll be using. Well, we've got another integration by parts. Here's our dv portion. And so our u is the ln of x. Our dv is the 1 over x squared dx, or x to the negative 2 dx. So take the derivative there. Integrate over here. Oops. And so we've got this becoming limit b goes to infinity of uv. So uv minus the integration of v du. There's our du, 1 over x dx. And so it looks like we've got negative ln of x over x plus the integral of x to the negative 2 dx. And then let's run that. That'd be x to the negative 1 over negative 1. So negative 1 over x. And remember, this was from 1 to b, right? So this is from 1 to b. And here we've got L'Hopital's right here. Here's L'Hopital's again. See how I've got negative, I'd be infinity over infinity. And so I'm going to run the derivative on that. So the negative stays in front. I run the derivative of the natural log. That's 1 over b. And then down here I also run the derivative of b, which is just 1. Minus, now as I run this to infinity, negative 1 over infinity, that's going to go to 0. So minus 0. And I got plus the natural log of 1, 0, and then plus 1. And so we've got a limit as b goes to infinity, negative 1 over b minus 0 plus 1. Well, as this runs to, that's really bad, infinity. As this runs to infinity, this goes to 0, and so we end up with 0 plus 1. So we get 1. Therefore, the improper integral converges again. Has a finite value of 1. All right, I got one more of these type 1 improper integrals, right, with an infinite limit of integration. So notice here we're going from negative infinity to positive infinity. And so what we want to do is, here, let me come back to the very beginning. This is type 1, but this is a number 3 right here. We're going from negative infinity to positive infinity. So what we're going to do is we're going to split it up. We're going to go from negative infinity to c, and then from c to infinity. You're just going to take c as some convenient value on there, and then you're going to examine it. So let me come back here. So this is a type 1, but a number 3 with an infinite limit of integration. So negative infinity, positive infinity, this function, we're going to split this up, going from negative infinity to c plus c to infinity. And here, you know what we'll do? Let's make it c be 0, just as a convenient value. So for us, we have negative infinity, positive infinity of e to the x over 1 plus e to the 2x. We're going to go from negative infinity to 0 plus 0 to infinity. Okay. And then what we're going to do is let me if you look at e to the x and notice the e to the 2x here. Let me come down here. If I think about u being e to the x, then what I would have is negative infinity to 0 of u over 1 plus u squared. And over here I'd have u over 1 plus u squared, right? And so here we have on the left, this is a type 1, but this is a number 2. I'm going from negative infinity to a value. This is a type 1, but 0 to infinity. This was the number 1 that we've been doing so many of right there. All right. And I should also note, remember that integral 1 over a squared plus u squared du is 1 over a arctangent u over a. Right? So let's go ahead and apply type 1 number 2. And so this will become the limit as a goes to negative infinity of a to 0 of 1, or I'm sorry, u over 1 plus u squared du plus, and here we've got type 1 number 1, so we're going to go limit as b goes to infinity, 0 to b, u over 1 plus u squared du, right? And then if you think about guess my apologies, I wrote this wrong. See how my du is ln of e to the x dx? So my du, here's my du, it's just a 1 on the top. My apologies, that's a 1 right there. That's a 1. Fix that. My bad. There we go. And so we've got 1 over 1 arctangent of u over 1, but our u is e to the x. So we've got arctangent of e to the x. And this is from a to 0. And then over here we've got limit b goes to infinity of the 1 over 1 arctangent of u over 1, or e to the x over 1. And this is from 0 to b. So we've got our arctangent e to the 0 minus the arctangent of e to the a, and then plus, now let's do it over here, we got a limit b goes to infinity, arctangent e to the b minus the arctangent e to the 0. And so we've got arctangent of arctangent of 1, that'd be pi force, minus, and then if we run arctangent of e to the negative infinity, if you want to think about that, that's like arctangent 1 over e to the infinity. So that's like arctangent of 0. And we know the arctangent of 0 is 0. Alright, let's keep going now. Now we've got the arctangent of e to infinity, which we know is that pi halves, right? It approaches pi halves as it shoots out, that graph, minus the arctangent of 1, which is pi force. Pi force, here, let me write it down here, minus pi force gone, so we got 0 plus pi halves, so this just all ends up being pi halves. So our improper integral does converge. And area under the curve from negative infinity to positive infinity is actually finite in pi halves, interestingly enough.